one-to-one functions, and inverse functions. In this example, we're asked to determine whether or not the function is one-to-one. Recall that in a one-to-one function, each y value is paired with exactly one x value. In other words, you cannot have two or more of the same y value. So if you were to pick points on the line and take a look at your set of ordered pairs, if you notice that you have two of the same y values, then it cannot be one-to-one. Now, another way to determine whether a graph is one-to-one is to do what is called a horizontal line test. If you sketch a horizontal line through your graph and it touches in no more than 1 point, then it is the graph of a one-to-one function. So let's go ahead and sketch our horizontal line. Now, in that first line that we sketch, as well as the second, notice it touched in more than one spot. So here's what's the first point where it intersected the line, and our horizontal line also intersected the graph at this point. So again, as soon as it's more than 1 point, then it is not a one-to-one function. So therefore, the answer to this is B. Choice B, no, it is not one-to-one. If the following defines a one-to-one function, find its inverse. If not, write not one-to-one. So here we're given a relation, a set of ordered pair relations. All we have to do is look at the ordered pairs and recall that you cannot have two or more of the same y value. So let's just first take a look at our y values. So we have a 7, we have a -6, we have a -5, and lastly we have a -4. Notice none of those y values repeated themselves, so therefore, yes, it is a one-to-one function. And if a function is one-to-one, it will have an inverse. So to find its inverse, all you have to do is simply swap your x and y values. In other words, whatever value that is in x's place will move to y's place, and vice versa. Whatever value that is in y's place will move to x's place. So when we do that, it will look like so. And there you have it. That is the inverse of the given set of ordered pair relations. In this example, we're asked to sketch the inverse of the graph given. All we have to do to sketch the inverse of this graph is to simply swap the x and y values on the graph and sketch. So let's take a few points from the graph, because all we need to do is just switch the ordered pair values, and you will have the graph of its inverse. And recall, when you do sketch the graph, it is going to be a reflection about the line y equals x, the identity function y equals x. It's going to be a reflection across that line. So let's go ahead and pick a few points on this graph. I'm going to pick -1, -9, 0, -5, 1, -1, 2, 3, and lastly 3, 7. Now all I need to do is just take these points, and whatever value that's in y's place, put it in x's place, and vice versa. Whatever value that's in x's place, put it in y's place. So when I do so, my new ordered pairs will be the following. And so now all we have to do is sketch it, and we will see that we will have the inverse of the given graph across, and it's going to be a reflection across the line y equals x. And here's that graph. Notice that our new line, the line you see there in blue, that is the inverse of the function given, and it is a reflection about the line y equals x, that line you see there in pink. And there you have it. We've just sketched the inverse of a graph given. In this example, we're asked to find the inverse of a function. We are given the function f of x equals 2x plus 3 over 5 and asked to find f inverse of x. So step 1 to finding the inverse of a function is to switch the x and y values. So let's first identify what that would entail. So here's our x value of our given equation. So this x is going to become y. Now let's look for y. Recall y, f of x is the same thing as y. So if this is y, it's going to become x. So when we do so, it's going to look like so. Our next step for solving this is to solve for y. Now to solve for y, let's first get rid of this rational number, or this fraction, we can call it. And recall, to clear fractions, you take the denominator and multiply both sides of the equation by the denominator. So in this case, our denominator is 5. We're going to multiply both sides of the equation by 5 so that, again, we can clear that rational number. So something from the top that matches something from the bottom. Recall, anything on the side is the same thing as being on top. Once we do that, we're left with an equation for which we're going to solve for y. Our first steps to solving for y is to subtract 3 from each side. Last step to solving for y is to divide by 2. Whatever you do to one side, you must do to the other. And our inverse function is f inverse of x equals 5x minus 3 over 2. Now you have two terms up top. You can also write it another way by simply placing their common denominator that they share, that 2. Place it underneath each term, and it can be written as 5/2 x minus 3 over 2. Either way is perfectly fine, but here we're going to go by the choices that we are presented, and so that would leave us with choice C as being the answer, and there you have it, finding the inverse of a function. Exponential functions, graphs, and evaluating functions. The properties of an exponential graph will have 3 specific points on its graph. So which one of the following points will pass through an exponential function? If you said choice B, then that is correct. The graph of an exponential function will have the following points: -1, 1 over b. It will also have a point on a y-intercept at 0 and up 1. And it will have a point 1, whatever the base b is. And there you have it, properties of an exponential graph. The graph of f of x equals 2 to the x was transformed to the graph of g of x equals 2 to the x plus 3 minus 4. Describe the transformation. Well, our pre-image is f of x equals 2 to the x, and if we look at our transform graph of g of x, Notice that behind the x plus 3, anytime you have the number with the x, that's going to signify that there was a horizontal shift. And since it's plus 3, that was a horizontal shift to the left 3 units. When you see a value in the back, that determines a vertical shift as to whether it goes up or down. In this case, because it's negative, it was a vertical shift down 4 units. So, which is the correct choice? You got it. Choice D. The graph was shifted 3 units to the left and 4 units down. Now, let's find the domain and range of g of x. So we're looking at the blue graph here because it was the one that was shifted 3 units to the left and 4 units down. Starting with the domain, that means how much this graph extends or spans to the left and to the right. Well, the fact that it has arrows on both ends means that it's going to go forever to the left and forever and ever to the right. So therefore, the domain would be from negative infinity to positive infinity. How about the range? How much it extends vertically? In other words, does it extend forever and ever up and forever and ever down? Well, no, it's not going to go forever down because notice you have your line, which is an asymptote, right at -4. So that's going to be the lowest point of this graph. However, it is going to go forever and ever up because it has arrows on the end to positive infinity. So therefore, our choice is C. The domain is from negative infinity to positive infinity, and the range starts at -4 and goes all the way up to positive infinity. And there you have it, the domain and range of an exponential graph. In this example, we're asked to evaluate the function f of x equals 3 to the x at x equals 6.1, and then round our answer to the nearest 10th place. Anytime you're told to evaluate a function and you are given the value of that variable, all you have to do is take that number and plug it in place of that variable. In this case, that variable is x, and they're telling you that x equals 6.1. So into the given function, you're going to remove the x and replace it with 6.1. Now you're going to take your scientific calculator and plug in 3 raised to the 6.1 power. And what you'll be given is an approximate number. And we're asked to round that number to the nearest 10th place, which means leave 1 decimal up. So if we leave 1 decimal up, we have here a 6. We need to move to the right of the 6 to determine whether we keep the 6 or not. So that number is a 5, and if it's 5 or more, it makes the number in front of it 1 more. So instead of 6, it's going to become 7. So it is approximately 813.7, and there you have it. Choice B, 813.7 is your answer. Logarithmic functions and properties of logarithms. In this example, we're asked to convert the exponential equation of 4 to the x equals 6.8 to a logarithmic equation. Now the first thing we want to do is take a look at the log form. For the log form, it is log base b of y equals x. So let's take apart the given function and find out which value goes where into the log function. So first of all, the 4, our big number, is called our base. So into the log function, you're going to remove the b and replace it with a 4. The other part of our given function, we have the exponent. The exponent is where x will go. So your exponent will go over to the other side on the right. Lastly, we have our answer, and our answer is the output, or what we would call our y value. So you're going to remove the y and replace it with 6.8. So when we put everything together, log form of this exponential equation would be which choice? You got it, choice A, log base 4 of 6.8 equals x. And there you have it. We have just converted the exponential equation to a logarithmic equation. In this example, we're asked to evaluate log base 6 of 1 without using a calculator. So you may say, well, how can I solve that without a calculator? Well, if you know the basic properties of logarithm, one specifically, which states that log base b of 1 equals 0, which means it doesn't matter what your base is, what that number is, but if you have log base of 1, it will always equal 0 by definition. So the answer to this one is simply 0. Now, if you're still pondering and wondering, is there another way to solve this? Well, yes, there certainly is. You can take that log and set it equal to x, and then convert it to exponential form. So let's do that circle snail-like pattern. 6 raised to the x power equals 1. So what number would you have to raise 6 to in order to get 1? Well, the answer is 0, because any number raised to the 0 power equals 1. So therefore, again, log base 6 of 1 equals 0. And there you have it, basic properties of logarithms. In this example, we're asked to evaluate the expression log base 5 of 5 without using a calculator. Well, we don't need a calculator for this. We can just simply use the properties of logarithms. One in specific which states log base b of b will always equal 1. So in this given log, my base, my b, is 5. So if it is 5 and of the number here is also 5, by definition it equals 1. Now if you didn't understand that, remember the other way is to take your given log, set it equal to x, put an x on the other side, and then rewrite it in exponential form. Let's do that snail or counterclockwise pattern. 5 to the x equals 5. So what you're saying is 5 raised to what power would equal 5? In other words, what number that I would raise 5 to in order to get 5? Well, in that case, we know it's 1. So therefore, again, the answer is 1 by just using basic properties of logarithms. In this example, we're asked to evaluate the expression 4 raised to the log base 4 of 20 without using a calculator. Now we can solve this without a calculator because one of the principles or properties of logarithms states that if your base of your log is the same as the base itself, when you have a number raised to a log, then it will equal x. In other words, it will equal whatever is behind that base of that log. So in this case, our base, our b, is 4. And notice that the log that the number is raised to also has a base of 4. And by definition, it will equal whatever you see right behind that base. In other words, that's your output. It will equal 20. Okay, and that's just by using what we call the properties of logarithms. There you have it. We're going to use another one of those properties to solve this particular one. Evaluate the expression log base 2 of 2 to the 10 without using a calculator. So looking at that property states that whenever you have a log to where your base of your log is the same as your answer, that is going to equal the exponent of that answer. So our base b here is 2, so is the answer. So it means that my output of my answer will equal whatever this exponent is. In this case, it is 10. So therefore, x equals 10, the value. And there you have it, basic properties of logarithms. In this example, we're asked to evaluate the expression log base 4 of 64 without using a calculator. We don't have to use a calculator for this because we can just simply rewrite it in exponential form and solve. So the first step to doing that would be to take the given log and set it equal to x. Next, we're going to move in that snail counterclockwise like pattern. So that's going to be 4 raised to the x equals 64. So I want to know what number do I have to raise 4 to in order to get 64. And that number is 3. So therefore x equals 3, and there you have it, choice D. In this equation, we're asked to solve the equation log base 3 of x equals -5. So the first thing we want to do is to rewrite this equation in exponential form so that we can solve it. So recall the snail or the circle counterclockwise pattern. That's going to be 3 raised to the -5 equals x. So you should note that anytime you have a negative exponent, you're going to have to flip it. In other words, that 3 is on top, but it's going to have to go on the bottom to make that exponent a positive. So we're going to go ahead and flip it. And so what we'll have then is 1 over 3 to the 5th power. Notice is positive now. And when I multiply the number 3 5 times, I'm going to get 1 over 243, and the correct answer choice is C. And there you have it, solving a logarithmic equation. In this example, we're going to solve a basic logarithmic equation. So we're going to first start by rewriting it in exponential form. So when we do so, remember that Snell's circular pattern is going to be 3 raised to the x power equals 81. Again, 3 to the x equals 81. So I need to know, what number do I raise 3 to in order to get 81? Well, the answer to that is 4, because when I multiply the number 3 4 times, I'm going to get 81. So therefore, x equals 4. Choice D. There you have it, basic log equations. In this example, we're asked to solve a basic logarithmic equation. So to solve this equation, we're going to start first by rewriting it in exponential form. So what we'll have is 2 raised to the negative 3 power equals x. So let's go ahead and write that. So recall that anytime you have a negative exponent, you must flip it. So once you flip it, you're going to have a 1 on top, 2 raised to the 3rd power on the bottom. Now your exponent is positive. So when you multiply the number 2 3 times, you're going to get 8, which leaves you an answer of 1/8. And there you have it, solving a basic logarithmic equation. All right, in this example, we're going to use the properties of logarithms to rewrite the expression given. Now, we're given a single log here, and when you're given a single log and asked to rewrite it using the properties of logarithm, you're probably going to be just simply expanding that log. Now, the other scenario you can have, and I believe that's the next problem, is when you're given it in expanded form and you're asked to write it as a single log. Okay, so let's focus on this problem. We want to expand it. So we're going to first start by removing the radical. So we're going to write the expression itself that's underneath the radical. We're going to write that as a fractional exponent. In other words, it's going to have an exponent of a fraction. So recall, I'm going to show you an example. For example, let's say if I have the square root of x over y. So if I have an expression like the square root over x over y, that would transform into x over y raised to the 1/2 power. And the reason you have the 1 on top of your fraction is because the whole radical itself, it was not raised to any power. Now, if it were raised to a power, that number would go up top. But since it wasn't raised to any specific power, we write a 1 up top. And because this is square root has an index of 2, so that is why you would have 2 under the bottom. Now let's focus here on back again at our example here. So that means for my fractional exponent, I'm going to have a 1 up top because the expression is not raised to, the whole thing would have to be raised to a power, and it's not. So I'm going to have a 1 up top. This is 5th root, so I'm going to have a 5 under the bottom. So when I rewrite it, it's going to look like so. My next step, since I have an exponent here of 1/5, by the power rule of logarithms, it states that you can bring this fractional exponent here, which is your exponent, bring it out front of that log. So when we do so, it looks like so. Next, well, let's focus our attention on this fraction. That's the quotient rule. So anytime you have a rational exponent or something in fraction form, That's the quotient rule, which is going to be top take away the bottom. So log of x squared minus log of y to the fourth power. And we'll keep that 1/5 outside. Next, you notice that these logs have an exponent. The first one has an exponent of 2. The other one has an exponent of 4. And that's the power rule, which means that we can move those out front of their log. So let's go ahead and do that. And lastly, we can go ahead and use the distributive property. 1/5 times 2 log x is going to be 2/5 log x. And then 1/5 times -4 log y is going to be -4/5 log y. And there you have it. We have it now in its expanded form. In this example, we're asked to express this log as a single log. So this time we're going to do the reverse. We want to write it as one single log instead of an expanded form of a log. So looking at what we're given, I see here we have a subtraction sign, which means that we're going to have the quotient rule involved. So it's going to be this log on top and this under the bottom, and log base b with the m on top and the n under the bottom. And I see plus you have a log in the back. So recall, when you have plus, you're going to wind up multiplying some logs there. I also see a 3 in front of the log, which that's something that I can move to the back of the exponent. But let's do one step at a time. So step 1, let's go ahead and consolidate these two logs into one log. Since they both have the same base, we can do that. So it's going to be log base b of, and then it's going to be m on top, take away the n on the bottom. That's called the quotient rule. Next, we're going to move that 3, that's a power rule, out to the back, which is going to be that exponent on that k. Good. And let's see, what else can we do here? Well, we have a plus sign, and a plus sign is the product rule, which states that if two logs have the same bases, that you can go ahead and multiply their terms. So what we'll have there using the product rule is log base b of m over n times k to the third power. Now you can also write it with k on the side or k on top, because recall that any number on the side is the same thing as being on top. And there you have it. Rewriting or expressing a log, an expanded log, as a single logarithm. Special logs and change of base formula. In this example, we're going to use a calculator to find the natural log of 0.983, and then we're going to round our answer to 4 decimal places. So what you'll need to do is get out your scientific or graphing calculator and locate the LN key and simply type in the natural log of 0.983. So once you locate that key, just type in 0.983, hit enter, and it should give you an approximate answer. And what you should see on your calculator are the following digits. Notice it is a negative value, but we are asked to round it to 4 decimal places. So let's count over 4. So the 0, that's 1, and then 2, 3, 4. So 4 decimal places mean that I'm going to leave 4 numbers up. So recall, I'm going to have to look at the number to the right of that 1. In this case, it is a 4. And I want to know, is that 5 or more, or is it less than 5? Now, because it is less than 5, we are simply just going to drop the 4 along with everything that is behind 4. So therefore, our answer would be C, negative 0.0171. And there you have it, using a calculator to find the natural logarithm. In this example, we're asked to evaluate the logarithm log base 3 of 25 using the change of base formula, and then round our answer to 2 decimal places. In other words, leave 2 numbers up past the decimal. So let's get started. Here we're given log base 3 of 25, and recall the change of base formula is as follows. For example, log base b of x is the same as saying log x over log b. You can think of it as kind of moving in a backward motion here. So you have the log, and then you have x, which would be on top, and then b is on bottom, so log x over log b. So using the given log we're given, it would be log 25 on top, and then moving backwards here, and log 3 on the bottom. So it will be log 25 over log 3. And from that point, all you need to do is just get your scientific or graphing calculator and type in log 25 divided by log 3, because you know that anytime you have it in fraction form or as a quotient, that it's a same thing as division. So go ahead and do that, and let's see what you get. So again, log 25 divided by log 3. Press enter. You're going to get approximation, and we want to leave 2 numbers up. So let's count over first at 3. 1, 2, 3, because you always count over 1 more than that place. Now, if this number, which is in this case is a 9, if it's 5 or more, which it is, it makes the next number in front 1 more. So you're going to have 2.93, and the answer is D. And there you have it, change of base formula. Evaluate the logarithm log base 5 of 50.48 using the change of base formula. Then round your answer to 3 decimal places. So recall the change of base formula is as follows. Log base b of x is equal to log x over log b. So plugging that into the given log, it's going to be log 50.48 on top over log 5 on bottom. Go ahead and input that into your calculator. You're going to press log 50.48 divided by log 5. It's going to give you an approximation, and you should see the following digits. And now we're going to round to 3 decimal places. So let's count over 4. 1, 2, 3, 4. So if that second number, 6 here is what we're looking at, if that number is 5 or more, which it is, it makes the number in front of it 1 more. And so what you're going to have is 2.437. And there you have it. Answer choice A, change of base formula. Exponential and logarithmic equations. In this example, we're asked to solve the following. 6 to the 2 plus x is equal to 36 to the x. So here we're given an exponential equation and asked to solve. So to solve this, we're going to use the equivalence property of exponents, which state that if b, x, and y are all real numbers and b, the base, is greater than 0 and not 1, then b to the x is equal to b to the y, which implies that if your bases are the same, that your exponents, you can set them equal to each other. So let's apply that property to the given problem. So first of all, what we need to do is we need to change the bases so that they are the same. In other words, rewrite the common base of one of them. Well, on the left side, we can leave that as is. But the right side can be written with a base of 6, because 6 raised to what power will give you 36? Did you say 2? Then if you did, that's correct, because 6 squared equals 36. So I'm going to rewrite the right side. Instead of the 36, I'm going to write 6 squared there. So when I do so, it looks like so. Now you still have that x out there. That didn't go away. Now what we're going to do is we're going to multiply on the right side 2 times x, which is going to give me 2x. And the reason for that is we wanted to get those bases alone by themselves. And now that we have them there, notice they are the same. And by the equivalence property of exponents, if your bases are the same, you can take their exponents and set them equal to each other. So we're going to set 2 plus x equal to 2x. From there, it's just a matter of solving for x, however you'd like to do it. Remember, there's no one way for solving. I myself prefer to get my variables on one side and preferably the left side, and my numbers on the right side, but it really does not matter. In this particular case, it's probably easier to subtract x from each side. And when you do so, you would see that x is going to be 2. So our solution then is 2, choice C. There you have it, solving an exponential equation using the equivalence property of exponents. In this example, we're going to solve an exponential equation. So recall step 1 is to find common bases. So I want to look at 64 and look at 32 to find what base number they would have in common if we were to rewrite them as exponents. So I can start with the smaller number, the 32, and right away I can recall that if 2 multiplied 5 times will give me 32. So that's going to be 2 to the 5th power. And I can also multiply 2, the number 2, 6 times, and then I'm going to get 64. So my base then would be a 2. So I would have 2 to the 6 is equal to 2 to the 5th power. Now I still have the other part of the exponents that were attached. But what we need to do now is use the distributive property to multiply them so that we can get the bases alone. So on the left side, that's going to be 6 times x, which is 6x, and then 6 times negative 3, which is negative 18. On the right side, 5 times 4x, and that's going to give me 20x. And now that we have the bases alone by themselves, by the equivalence property of exponents, we can take their exponents and set them equal to each other. Bring our exponents down, in other words. So I'm going to have 6x minus 18 on the left side and 20x on the right side. Now it's time to solve for x, however you'd like to do it. Since the larger variable is on the right side, I can proceed by subtracting 6x from each side, then divide by 14. And once I simplify my answer, and recall that a positive divided by a negative is going to be a negative. So anytime the top or the bottom is negative, it makes the whole fraction a negative. Just make sure you simplify your answer. So when we simplify and take out the common factor, we're left with negative 9/7, and that is your answer. In this example, we're going to solve an exponential equation. Step one is usually to find common bases. But we don't need to do that for this one, because if you look at the given equation, on the big number, the base on both sides is e. So since they have the same base, all we need to do on the right side then is just to use the distributive property so that we can get e alone. So that would be 4 times x, which is negative 4x on the right side as your exponent. And now that we have our common bases there, we can go ahead and bring our exponents down, because recall the equivalence property of exponents states that our exponents will then be equal to each other. So that's 5x minus 1 is equal to negative 4x. We want to go ahead and solve for x. I'm going to add 4x to each side, and I'm also going to add 1. When I do so, that will leave me with 9x equals 1. Last step to solving this then is to divide by 9. And x equals what? You got it, 1/9. And there you have it. Answer choice B. In this example, we're going to solve an exponential equation. So step one would be to find common bases. So you can't break 3 down. So we look at 12, and can you have a base of 3 and somehow produce a 12? Well, the answer to that is no. You can even test it by saying 3 squared, that's going to give you 9. 3 cubed, that's going to give you 27. You're already over. So you cannot create like bases with this. So let's use some other method. How about if we use the change of base formula? So when you don't have a common base, then one method you can use is called the change of base formula. So rewrite it back as a log, and recall how we converted from log to exponential and then exponential to the log. We did that in an earlier section. So to create something in log form, log base b of x. So our base here would be 3, so that's going to be log 3. Our answer here is 12. So it's going to be log base 3 of 12 is going to equal x. So there you have it. Now let's use the change of base formula. Remember, with the change of base formula, it's going to be log 12 on top and then log 3 on bottom when you rewrite it. Get your calculators out. Go ahead and key that into your scientific or graphing calculator. Log 12 divided by log 3. You should get an approximate answer. And you should have gotten these digits. And which one of those choice when you round it to 3 digits? You got it. Choice B. There you have it. Solving an exponential equation that does not have a common base using the change of base formula. Let's look at another way we could have solved that problem. So again, our given problem was 3 to the x is equal to 12. We could have also took the natural log of each side. So again, when there's no common base, you can take the natural log of each side. And we still want to solve for x. That's with any case in solving an equation. Now, by the power property, when you have an exponent here, recall we can bring that exponent out in front. So let's go ahead and do that. That's a power property. Again, we want to solve for x. So to get x by itself, right now x is being sandwiched with or multiplied with the natural log of 3. So what we have to do is get rid of the natural log of 3. The opposite of multiplication is division. So I have to divide by the natural log of 3. And recall with equations, whatever you do to one side, you must also do to the other side. So what you're going to have then is x equals the natural log of 12 over the natural log of 3. So now you're ready to get your scientific or graphing calculator out, and you're going to type in the natural log of 12. So find the ln key and then type 12 divided by the natural log of 3. Enter. It's going to give you an approximation. And rounding that to 3 decimal places should give you which choice? You got it. B. That is correct. In this example, we're going to solve a logarithmic equation. Solve the natural log of x minus the natural log of x minus 6 equals the natural log of 9. So first, we're going to rewrite the left side as one single logarithm, because notice here we have one log, take away another. We can use the quotient property and rewrite it as the natural log of x over x minus 6 equals the natural log of 9. And now we can use the equivalence property, which states that when the bases are the same, and it is the natural log here, the basis is the same, we're going to bring the expression down of x over x minus 6 equals 9. To solve for x here, we can cross multiply. On the right side, we can write 9 as a fraction, 9 over 1. And then once you do so, just simply cross multiply each side. 9 times x minus 6 equals x. And from there, keep solving for x. 9 times x, and then 9 times negative 6 on the left side. Next, subtract x from each side, and then add 54. Last step to solving this is to divide by 8. And x equals 54 over 8. We can simplify that, take out the common factor there, and that's going to leave us with an answer of 27 over 4. And there you have it, solving a logarithmic equation. In this example, we're going to solve another logarithmic equation. Log base 5 of x plus 2 plus log base 5 of x minus 2 is equal to 3. Well, the first thing I want to do is to rewrite the left side as one single log. So we have two of the same log, log base 5. So we can use the product rule to rewrite that expression. So once we do so, remember when you see two logs that are split up and they're added together, that is the same as bringing them together as one log and then multiplying them together. So once we do so, it's going to look like so. Our next step is we're going to rewrite the equation in exponential form so that we can solve. So recall the snail-like circular pattern or counterclockwise, starting with the base 5 raised to the third power equals the binomials of x plus 2 times x minus 2. And what that is nothing more than a difference of square. We can write that in short form as x squared minus 4. So we have 5 to the third power. When we multiply the number 5 3 times, we get 125. And on the right side, we have a difference of square. Next, we're going to add 4 to each side so that we can isolate the squared term. Our next step to finding x, to solving for x, is to simply take the square root of both sides. Whatever you do to one side, you do to the other. And x equals the square root of 29. And there you have it. In this example, we're going to solve a logarithmic equation. The natural log of e to the x minus the natural log of e to the 7th equals the natural log of e to the 4th power. So the first thing we're going to do here is use the power property to move the exponents out front. So we're going to move the x, the 7, and the 4 of those exponents out to the front of their log. When we do so, it looks like so. Now notice here what we have is the natural log of e with each one of these terms. And recall that the natural log of e is equal to 1. In other words, log base e of e equals 1. So everywhere you see the natural log of e, you can simply cancel those out because they're going to equal 1. And so what we're left with is just simply x minus 7 equals 4. Last step to solving this equation is to add 7 to each side, and x equals 11. And there you have it, solving it using the shortcut method. In this example, we're going to be finding the pH. So the formula for the pH of a solution of hydrogen ions is given by the logarithmic equation. The pH is equal to the negative log of the solution's hydrogen ion concentration, where H3O plus is the hydronium ion concentration. So find the pH of a certain agricultural product with the hydronium ion concentration of 1.0 times 10 to the negative 5. So since we were given the hydrogen ion concentration, all we have to do is go plug that into the place of the H3O plus. So let's go ahead and do that. Now actually at this point you can use your scientific or graphing calculator and simply plug in the negative log of 1.0 times 10 to the negative 5 and get your value automatically. Or you can do it by hand as well, just using the properties of logarithms. So recall that whenever you have the product rule states when you have a multiplication of two logs, if you want to rewrite them, you can write them as the addition of the two logs. Let's find the value of each log. Now notice here with these two logs, you don't see a base. So when you don't see a base, it's assumed that it is a base 10, which is the common log. So if we look at the first one, that's just your basic property of log base 10 to the 1. Anytime you have a log base of 1, it's going to equal 0 because that's the only number, any number raised to the 0 power is going to give you 1. So x then will equal 0. The other one is the basic property. Recall that if your base is the same as your answer here in your log, that is going to equal the exponent there of the log. So x then will equal -5. So plugging those two values in, and we have a negative there, so a negative in front of it. But inside the parentheses, it's going to equal -5. 0 combined with -5. And -5, but with a negative in front of it, becomes +5. So then we would say that the pH of a solution with a hydrogen ion concentration of 1.0 times 10 to the -5 is approximately 5. And there you have it, finding the pH. Let's do another example there. The formula again for the pH of a solution of hydrogen ions is given by the logarithmic equation, and we are given a hydrogen ion concentration of 2.4 times 10 to the -10 power, and we want to round our answer to the nearest tenth. So we're going to go ahead and plug in the values that we've been given. And again, at this point, you can just simply use your scientific calculator to calculate the value, or we can do it manually. So let's go ahead and, using the product property, we're going to rewrite this as an addition of two logs. And then calculating each log, again, you can do that on your calculator as well, or you can do them just knowing the base formula, basic formulas of logarithms. When you get those values, you're then going to combine the two values that are inside the parentheses. That's going to give you a negative, but with a negative in front of it is going to give you a positive. And so the pH of a solution with hydrogen ion concentration of 2.4 times 10 to the -10 power is 9.6. Compound interest formula. Find the amount in a savings account at the end of 8 years if the amount originally deposited is $7,000 and you leave it in there, don't touch it. The interest on it is 5% compounded quarterly. So how much would be in the account at the end of the 8-year period? Well, we can use the compound interest formula to find that, how much would be in that savings account at the end of the 8-year period. So let's use everything we know. We were given, let's see, 8 years, that's your time. We were given the amount deposited, the principal amount, that was $7,000, that's P. We were given the rate. The percentage here is 5%, which when we turn that into a decimal, recall it's going to be 0.05. And how many times it was compounded? Quarterly, so that's 4 times a year, so N would equal 4. So plugging in everything we know, at this point, I mean, you could just use your scientific calculator or graphing calculator and just simply do all of this in one input. Type in 7,000 parentheses 1 plus 0.05 divided by 4, close parentheses, raised to the 32 power, because 4 times 8 is 32. And the calculator will give you the value. You don't have to do that by hand. And the value you should get is $10,416.91 once you round it to the nearest cent. There you have it, compound interest formula. How long would it take for $800 to grow to $36,700 at an interest rate of 11.5% if the interest is compounded continuously? Round the number of years to the nearest 100. So the key to this problem here is compounded continuously. Now that's different from the previous problem that you worked on. When you see that it's compounded continuously versus being compounded quarterly, annually, semi-annually, when you see continuously, you're going to use the formula A equals P times e to the RT. Now the A and the P are going to be the same as the previous formula that you use. A is your future value. In other words, let's interpret this problem. We have $800 that is being put in an account, and we want it to grow to $36,700. In other words, we want to leave it in the account, don't touch it, let it grow interest at a rate of 11.5%, compound it continuously until it gets to $36,700. So our A stands for our future amount, so we want it, that's going to be the $36,700 that we want it to grow to. Our P is our principal amount, the amount that's put in. It's also called the present value, and that is the 800 that we started with, that we put in. The R, our rate is 11.5%. If we move that decimal place 2 places over, it's going to be 0.115. The T in our formula stands for the time. We don't know that, so that's what we're going to be solving for. Now the E in there is just the inverse of the natural log. So let's get started by plugging in everything that we know to find out what we don't know. So once we plug in the formula, it's going to look like so. So step 1 is to, on the right side, we want to get the E by itself. Now E is being, e to the 0.115t is being multiplied with 800. Notice they're sandwiched together, so they're being multiplied. So the way I get rid of the 800 is I have to do the opposite. The opposite of multiplication is division, so I have to divide by what I want to get rid of. So I'm going to divide by 800, and recall the rules for equation. Whatever you do to one side, you must also do to the other. So on the left side, I have 36,700 divided by 800. I can go ahead and perform that operation. And what I'm going to be left with is 45.875. And on the right side, e to the 0.115t. The next step to solving this equation is I want to take the natural log of each side so that I can cancel out that e. So once I take the natural log of each side, recall that the natural log of e is equal to 1. So when that cancels, that's going to leave me with just simply 0.115t on the right side. Last step to solving for t, getting t all by itself. Notice it is being multiplied with 0.115. The opposite of multiplication is division, so I need to divide by 0.115. Whatever you do to one side, you must do to the other. When we do so on our calculator, take out your scientific calculator or graphing calculator, and you're going to type in the natural log of 45.875 divided by 0.115. And what you should get is an approximate answer here. And rounding that to the nearest hundredths place will give us which answer? You got it, choice B. And there you have it, compound continuously. In this last problem, we want to know how long will it take for prices in the economy to double at a 9% annual inflation rate. Round your answer to the nearest year. So, and we're also going to use the A equals P times E to the RT formula whenever we want to find out how much something has doubled or increased over a period of time. So plugging in everything we know to find out what we don't know. We know the interest rate is 0.09 when we convert it to a decimal. Double, when something doubles, it's twice that. So when we rewrite this formula, what we're going to have to write it as is A equals 2P. So the amount is not just a single amount, it's going to be twice that. So writing that at your new formula now is going to be 2P equals P times E to the RT. Because again, we're doubling it, that amount, not just one single amount. Let's go ahead and plug in our rate. So our next step for solving this equation is we want to remove the P, in other words, get E by itself. To do that, we're going to have to divide by P. So whatever you do to one side, you do to the other. Now that we have the E isolated, we're going to take the natural log of each side. Our next step to solving this is we're going to go ahead and cancel out the natural log of E, because recall the natural log of E equals 1. So we're left with 0.09 t on the right side. Last step to solving for t is to divide by 0.09. Whatever you do to one side, you must do to the other. And on your scientific or graphing calculator, you're going to type in the natural log of 2 divided by 0.09. It's going to give you an approximate. And you're going to round it to the nearest whole year, which will be 8 years. And there you have it. Okay, that's it for this review. I hope you found it to be helpful. Stay positive, stay focused, study, and make it happen. But most of all, thank you for watching math videos on PowerPoint tutorial with Dr. Speights. Please like, share, and subscribe.